This lesson has been developed in the framework of SCILED project.
Module 3, Footwear Design Engineering. Unit 3, Engineering Footwear for Mechanical and Hydrothermal Comfort.
Lesson 3.3, Managing Shock Absorption Characteristics. This lesson is structured as following. Introduction. Factors affecting mechanical interactions between foot, sole and ground. Evaluating shock absorption and cushioning by FAA.
Introduction. Besides loading and the distribution of plantar pressures that may cause discomfort and pain, cushioning and shock absorption are also fundamental to good quality footwear that protect the user from sudden loading while moving or working. There are two major approaches in the scientific literature, one coming from the field of biomechanics and one from the field of ergonomics. In biomechanics, the burden is on the characteristics of the structure to reduce forces that have the potential to cause injury. This is the case for pure shock absorption. On the other hand, in ergonomics, the focus is on material compression characteristics related to fatigue effects and discomfort.
Factors affecting mechanical interactions between foot, sole and ground. Ergonomics is more concerned with cushioning comfort for the user. A thorough study of the ergonomics of cushioning was performed by Gundlach, 1999, who proposed metrics of material hardness, compression and deceleration on foot impact on the ground. Instead of deceleration, rebound resilience or percentage energy lost can be used, extracted from stress-strain hysteresis graphs. If recovery time for the sole material exceeds gait cycle time, then residual compression affects sole mechanics.
If recovery time for the sole material exceeds gait cycle time, then residual compression affects sole mechanics. Up until now, studies of compression phenomena incorporating resilience characteristics has been very limited on specific structures and, thus, are of no major practical significance. For most footwear professionals, the biomechanical approach on managing maximum values of forces on foot impact on the ground is more manageable.
An interesting finding reveals that increased stiffness of the footwear sole structure leads to lower strain energy and, therefore, lower capacity for shock absorption. This is shown in figure, where high values of plantar pressure, typically generated during walking and running, cause deformation of the sole structure, and it appears that soft materials, for example natural crepe, polyisoprene, have an excellent potential for absorbing the strain energy of the compression. Successful shock absorption, therefore, requires the incorporation of materials of lower stiffness, for example, EVA, PU foams etc.
On the other hand, it has been observed that the stiffness of the sole has no effect on the maximum bone stress. Bones are not affected by the nonlinear mechanical characteristics of the contact surfaces, and their stress depends only on the weight of the person and the properties of the soft tissues. Practically, this means that even the most shock-absorbing shoe cannot fully protect an overweight person with weak foot musculature. Footwear is always an aid to safer standing and walking, not a solution that blankets underlying health issues.
The geometry of the sole also influences the mechanical interaction with the plantar surface of the foot. It affects the fitting of the foot to the shoe and the resulting extent and shape of the contacting. Sole thickness also affects energy absorption, which is expected in engineering theory. It is even practically known in the safety footwear industry that thicker soles cut vibrations, so soles designed for such environment are thicker than for equivalent casual footwear.
Evaluating shock absorption and cushioning by FAA. Managing shock absorption characteristics through virtual tools is possible today with solutions ranging from multivariate analysis to finite element analysis. Though for most leisure casual footwear, for example, slippers, clogs, pumps, high-heeled shoes, shock absorption is not an issue, it is critical for products in the sports and occupational sectors. The designer has to examine footwear sole models with the use of a human foot biomodel for cases ranging from standing to fast movement. Heat loading has to be avoided as described in the plantar pressure management guidelines. Maximum plantar force values are a simple yet sufficient measure for evaluating shock absorption, and they are used in many studies. In addition, strain energy absorption levels have to remain high if an absorbing structure is to be produced. According to literature, the result above 0.5 J per cubic millimeters for 0.2 megapascals of vertical plantar pressure is more than sufficient for most purposes.
Modeling soft tissues as hyperelastic materials is necessary to accurately calculate the plantar pressure distribution. The use of linear elastic material properties may lead to significant overestimates of plantar pressures. However, this may increase complexity, time to convergence, solving of the equation systems, and burdens optimization simulations.
A quite interesting approach, feasible through finite element analysis, incorporates the concept of strain energy density, which is the quotient of the energy stored in a structure during deformation over the volume of the structure, excluding any voids. This was first incorporated in the OPT Shoes Virtual Assessment Toolkit in 2016, and it has been used for both academic research and commercial assessment of sole designs.
Kalaki et al. 2015, have investigated the effect of materials on the layers of the sole on shock absorption. The biomodel of the human foot utilized in that work assumes that bones are bonded together into the soft tissue. 3 finite element models are created to simulate the 3 major gait phases during walking, i.e. heel strike, mid-stance and toe-off. Linear elastic materials were used for their analyses. Material properties for bones and soft tissue are 7.3 gigapascals and 1.15 megapascals, respectively. Concerning the sole material, a number of material combinations are used. Soles consist of 2 layers, as it is presented in figure, and they are modeled with the insole having a thickness of 5 mm, and on outsole having a thickness of 10 mm. The major material combinations used are leather/natural rubber, hard, EVA/PU double density, middle, and PU foam/cork, soft. The upper part of the foot is fixed, and a stepwise displacement is applied at the lower sole surface.
By running the corresponding finite element analysis, the applied forces, reaction forces, and the plantar pressure distribution is calculated. As it is shown in figure, the shock absorption decreases with decreasing sole stiffness. This decrease is almost constant for all gait positions. The PU foam/cork combination gives the best results to the reduction of the plantar pressures, respectively better shock absorption properties.